Now, after we spoke about the Langevin equation, let's take a bit of a step back and discuss what happens when there is no noise at all in the system. Let's look again at our model that I repeat here in equation 17. Now, if we recall our discussion of the Langevin equation, we can look at the drift term in this equation and identify it with the minus the derivative of the potential. Therefore, we directly read off the drift potential u of x that corresponds to our model. And it's given here in equation 18, and it has the form of a fourth degree polynomial in x. And this is a potential function of a quartic oscillator because of the fourth power of the potential. Now, for various specific cases, this potential reduces to some of the most famous problems in physics. It has three parameters, theta, kappa, and g. Respectively, you can set any of these to 0, and you can also change signs of parameters in this potential. For example, if we take theta negative and set kappa and g to 0, we get the potential of a harmonic oscillator. If we take g to 0, we get the Verhulst potential. And if we take kappa to 0 and leave two parameters theta and g, we can get two interesting cases. One of them is when theta is negative and g is positive. And this describes an anharmonic oscillator with quartic nonlinearity. And another case is obtained when theta is positive and g is positive. This potential is related to one of the most interesting phenomena in physics that is called spontaneous symmetry breaking. And we will talk about this phenomenon a bit later. For now, let me show you some examples. But before doing that, though, I want to show you an equivalent form of the same quartic potential that uses a different parameterization. And this is shown in equation 19. And instead of parameters kappa and g, here we have two other parameters, a and b. And these parameters specify positions of 0 of the potential, as you can see directly from the formula itself. Also, you can also easily find the relation between these two sets of parameters that is shown in equation 20 here. Now let's go back to examples. In this first example, I show you a potential that is obtained if we take theta less than 0 and parameters a and b positive. The potential has two minima. The minimum at x equals 0 is a local minimum, where the minimum at approximately 3.5 is a global minimum. In between of these two minima, there is a maximum at approximately x equals 1.3. It's interesting that if we keep the same combination of parameters theta negative and a and b positive, but change the variable to log price, y equals to log x instead of the price x, then the change of variable is not quite mechanical, because this potential and the one in the x space is based on the actually on Fokker-Plan equation that we will discuss later. But I want to show you the result now because we will use it later again. So if we switch to log price instead of the price, which we can do if we want to model non-negative prices, now the potential in the new variable goes to negative infinity, actually linearly for large negative values of y, as y itself goes to negative infinity. And this means that the fall to the center in the original x space can be equivalently described as an escape to a negative infinity under a force that becomes asymptotically linear in the log space. Now, another type of dynamics is obtained if we take theta positive and a and b also positive. And in this case, a typical potential is shown in this graph. Here I temporarily return to the original x space instead of the log price space y. For such potential, we have a metastable state at x equals 0. If a particle is initially placed somewhere near this point, and released, it can escape after some time over the barrier to the left or the barrier to the right. And if it crosses the left barrier, the particle can escape to a negative infinity. But if it first crosses the right barrier, it can escape to a positive infinity. And finally, one more interesting scenario is obtained if we take theta larger than 0 and A negative and B positive. In this case, you will also have a potential similar to what is shown here. And in this case, the point x equals 0 would be an unstable point rather than a stable or metastable point. It's unstable in this case because it's a maximum rather than a minimum. Therefore, even a tiny perturbation completely knocks out a particle that is initially put at x equals 0 in such potential. And if we don't allow this particle to go to negative value, we can put reflecting or absorbing boundary condition at 0. The particle can then move to the right from the point x equals 0, and initially its potential will look like an inverted harmonic oscillator potential of the GBM model. So initially the motion looks like an exponential expansion. But such exponential expansion does not continue indefinitely. Once the particle approaches the global minimum point around x equals 3, it slows down until it settles at this global minimum. Now, this scenario may bring in one's mind several possible analogies. On the physics side, it reminds some theories of cosmology called inflationary models. It's also related to a very beautiful physics of the so-called Higgs bosons. If we come back to finance, then, as we already said, it reminds us the inflationary behavior of the GBM model. Imagine, for example, that we are mostly interested in small values of the stock price around 0 and take a linear approximation to a general nonlinear drift function around this point. In this case, if we use multiplicative noise, that is the diffusion term that is linear in x, we would obtain the GBM model as a result. So if we are unaware that this linear dynamics is only an approximation to nonlinear dynamics, then we might expect that a period of unbounded exponential growth will continue indefinitely. But this picture shows that if the full model is nonlinear with a true potential as in this graph, then this will just be an illusion. After a while, an exponential expansion will slow down and the system will achieve a non-trivial steady state.